All right, so let's start talking about security engineering. There's a whole lot of topics here, but the only thing I'm going to talk about now is security models, which is interesting and it helps you understand the history of the theory of security. And I was very interested to learn this the first time I studied the CISSP. I'd never heard of this before. So here's the security models we're going to talk about. And the most famous ones are Bell, LaPadula, Biba, and Clark-Wilson, but there are quite a few others available. But this is where we tried to define what security is in times like the 80s and 90s. Computer scientists tried to figure out what security is. And so they're going to use this concept of down and up. Up is up your levels of security to a more restrictive security classification like top secret, and down is moving to less classified stuff, like moving from secret to confidential or secret to unclassified. So that's what we mean by up and down. And so this is the simple security property. This was the first thing. The first thing people thought of is you don't want to leak out the secrets. So there's no read up, which means subjects with low clearance cannot read data at high clearance. Now that's what you mean. If you're not top secret classified, then you're one of these lower levels, you should not be able to read the top secret information. That seems obvious. And so that is the obvious security property, the simple security property, and the Bell-LaPadula model was defined to try to make computer security based on just this rule. And this turned out not to be good enough, but it does protect confidentiality. The problem is it doesn't stop writing up. And of course, you might need to write up. You might take information that was produced by your low-level staff and then make a document including that information that becomes classified. That's writing up. But what that means is this does not violate confidentiality. Someone with a lower level could discover something which is then classified and passes beyond their clearance. That does not violate confidentiality. However, you cannot write down. You can't take top secret data and write down to secret machines. What you would have to do is go through a formal process of declassifying that data, and then it would no longer be top secret, and then you could put it down. And that if you could move it without it being declassified first, that would violate confidentiality. So far, all of this makes sense. And people with top secret clearance can read lower things. That's allowed. That obviously doesn't violate confidentiality. You can read things at your level of clearance or lower. All right, that's this system of down and up. That's the Bell-LaPadula model, but the only thing it provides is confidentiality. All right, now there's a state machine model where you have a mathematical model of your system, all the files and all the users and such, and you have interaction between them, and that's a state. And a certain state is when certain users are accessing certain documents, and when users access different documents, that's a different state. And so what you want to do is arrange a security system so every possible state is secure. And every attempt to reach an insecure state, such as a low clearance person reading a high clearance document, you have controls that will block that. That's the idea. All right, so the Bell-LaPadula model was developed for the Department of Defense, and they were thinking about confidentiality. It has two rules: no read up and no write down. So people with low clearance can't read high clearance documents, and people with high clearance cannot take the high clearance documents and write them to a low clearance location. So those two are the rules that are enforced in the software. And they wanted to see how well this worked. And it turns out that you do get confidentiality, but you do not maintain integrity. Because a low clearance operative can write up bad data. They can submit false data, which moves up to high clearance level. Nothing in the model prevents unauthorized alteration of high data. Nothing prevents write up from corrupting the data, even though the low privileged person is not able to read that data. So it does not protect integrity. And this is, I think, how they discovered that there's more to security than confidentiality. The first thought is all security is confidentiality. But then when they built this system and saw how it worked, they said, well, we also have to have other security property called integrity, which is not provided by this model. So there's a tranquility property, which says security labels don't change while the model is operating. And there's a weak tranquility where the labels can change, but they don't change in a way that will violate your security policy. Anyway, then there's lattice-based access controls. It's another system. Subjects and objects have various classifications like clearance, need to know, and role. And subjects have a range of access. Their least upper bound and greatest lower bound. And there's this highest level of access is called alpha, beta, gamma. And they have a sort of complicated structure here of various kinds of security permissions that various different people would have that would let them access different data. I never used this system, but I've heard about it in the book. But the BIBA model is the next one, which goes after the LaPadula. So the LaPadula model protected confidentiality but not integrity. So the BIBA model is just the opposite. Reverse both axioms, no read down and no write up. This is the simple integrity axiom. Therefore, the high clearance level cannot read things at lower clearance level, so they can't get the bad data from lower levels, corrupting them. And no write up means low-level subjects cannot change the high-level data. And when I think about this protects integrity but not confidentiality. Then this helps you understand what we now understand, that integrity and confidentiality are opposing goals. You can't have both of them perfect at once. And the example I think about here is the Catholic Church. The Catholic Church has this thing called the Bible, and nobody can ever change it. Nobody can write up. And it's the highest level of data within their structure, but everybody can read it, and nobody can change it. And I think that's what you have here. You have integrity. You have this document that will never change, and everybody at every level can read that document. So you have integrity, but you have no confidentiality. Everybody can see it. So anyway, all right. Clark-Wilson is finally what came later, where you try to have a real-world model that will give you an appropriate level of both of these properties that you want. So subjects access objects by programs, and the programs work by well-formed transactions and separation of duties are their concepts here. So well-formed transactions are things that take unconstrained data items and turn them into constrained data items. So you have data that comes from outside, like user input, which may or may not obey your security policy, and you have a transaction procedure that will take that untrusted, unconstrained data and apply constraints to it. Like, people give you data, like they send you letters, and you read the letters, and then you decide what classification level they have and put them in the structure. That's the transaction that will take this unconstrained data item and move it into your constrained structure, where now it's controlled who can access it. That sort of thing. And then there's separation of duties, where you have, you don't let one person do a dangerous thing. One person will propose to do it, and that proposal will be reviewed by another person before the action actually takes place. That's separation of duty. Two people must work together to do something like issuing payments, and therefore it's less likely that one person can make a mistake or commit fraud. They would have to have a conspiracy between two people to do that, and that's more difficult. All right, those are a few concepts. All right, let me get to 3A here in the cahoots, which is up here. All right. By the way, I'll mention the mnemonic I used to take this exam. The three main models are in alphabetical order: Bell, BIBA, and Clark-Wilson. And they are in a logical order. The first one protects confidentiality, the second one protects integrity, and the third one balances the two, and is therefore the one you can actually use. Anyway. All right. All right, so which security model gives you confidentiality but not integrity? Yep, the Bell one. First one in alphabetical order. That was the one that had, gives you confidentiality, but he didn't think about integrity at that time. All right, what security model has this alpha, beta, gamma stuff? You notice, by the way, that I understand almost nothing about how this works, and neither do you, and that's fine. Remember from the first class, the CISSP is a mile wide and an inch deep. You just learn a little bit about all these concepts, no depth. So that's the lattice one. Anyway. All right, what security model enforces no read up? That's bell lapadula, that's confidentiality. People at a low level cannot read the high classified data. So that's confidentiality, that's the Bell model. All right. All right, which security model enforces no read down? That's BIBA, the second one, that gives you integrity. And so the point is, the first one is the extreme confidentiality, but no integrity. The second one is extreme integrity, but no confidentiality. And the Clark-Wilson is when you compromise and have a reasonable system you can live with that gives you some level of both of those properties. All right, anyway. All right, it's on you. Clark. All right, let's stop the recording.